Hello, everyone. This is Mathman, and this is a problem that I got from a YouTube site, Presh Talwalker, and it was a particularly difficult problem to solve, even though it looked like it may have been simple. I went to a different mode of solving this problem, and in the next video you'll see how I did it. These two first sheets are my scrap sheets on how I did the work. You can always come back to these sheets and take a look at my solution. So I just wanted to provide them for you as a resource.
Okay, now here is an interesting problem from Presh Talwalker. He's one that's got a lot of these math problems for you to solve, and he's got some highly ridiculously difficult ones to solve, and they look simple at first, and then you find out after you get started on it that it's a little bit more difficult than you think. What I put here is a little bit more than what they start the problem with. And this is going to be a little difficult to draw, but basically what I'm going to do is just give you an idea of what beginning information they give you. Now, I don't know how to get this darn thing narrow. I don't know how the well, only when you don't want it to do what you want it to do does it do it. Well, anyway, we can still get an idea. All right, what we're going to do imagine this is an isosceles triangle, which it is, and this is it's a lot taller in imagination than what you start with, more like the figure I showed before. And then you got a line that goes over from here, from this corner up to the line, and then this corner up to that. You got to make believe that this is a tall, narrow triangle. Use your imagination. Just get rid of some extraneous stuff. And what you're given is you got this, you got 20 degrees, you got 60 degrees. I forgot the last piece of it. And All right, so we got, oh, let's make this a little neater, even though it's kind of a crappy image. All right. Now you start out, remember this is going to be a lot taller and narrower than in reality. So this is 20 degrees. This is 60 degrees. This is 70 degrees. And this is 10 degrees. This is all you're given. That's all you're given, except that it's an isosceles triangle, because both of the base angles are 80 degrees. This is 80, and this is 80 degrees. So, given that, we know that we've got 50 degrees here. We got 50 degrees there. This is 130, because 50 plus 130 is 180. So this is 130. And we have sum of 140, so this is 40. And then this one is 150 plus 30. So we got all the angles. And what you're trying to find is, what is this angle? And basically what they do is they give you some approaches. The way he solves it, he goes, I think, from here to there, and I think there may be more. I don't know if he goes from here to there, but that could be one of them. And so basically he starts solving for angles and stuff, and so this we know is 70 degrees, and so this has got to be 110, and we don't know what this is, so we're going to call it phi. And there are different ways of finding the angles, and he uses in his approach, he uses a similar. He says that this angle, I think we know that phi, phi plus alpha equals 80, and we're using similar triangles here. We know this is 80, and so somehow they get x plus 30 plus 80. They use phi, I think, is equal to x plus 30, but to me, that's not a given. There's no similar angle. I'm gonna make this a little more clear. That's an alpha. And to me, it wasn't obvious that that was the case, that we had similar triangles. And yet that's the way he approaches it. Now, what I did was I started out with, well, I got an arbitrary base M sides L. I don't need this to confuse. And I used similar triangles and the law of sines, Q, and I called this I called these different lengths, and I called that S, and I called this A, and I called this Z, and this I called F, and I think this I called W, and P, and T. The whole side is L, and I called this T, and I called that V, and this is V, and I called this I forget what I called this side, but anyway, that was the approach I took. I assigned an arbitrary M equals 10. And what that does, then I can find L using trigonometry, and I can find Q and A and S, W, all using the law of sines. So that's what I did. Instead of trying to make similar triangles, which were not obvious to me, it just wasn't obvious to me. I tried different ways of trying to figure that out. I don't know how they figured that out. So I just wasn't satisfied with that. I tried and I worked on it, and I couldn't get it. And maybe it's just me, but I just wasn't able to do it. So I did what I said there. I assigned M equals 10, and then I got L equals 28.8, and I just worked from there. And what happened is I just worked my way all the way up to get the different lengths. And so basically I resorted to the law of sines, and in one circumstance, I used the law of cosines. And you know what? I got an answer. And I got a very, very, very close to the answer that they got. In fact, when they rounded it out, I ended up getting the exact answer. So, with that in mind, and knowing that I have the that isosceles triangle, I had assigned different lengths. And so basically I started with the law of sines, and I started out with M equals 10, and then L equals, and I had L on sine 80 equals M or 10 on sine 20. Because when you have an isosceles triangle where the base angles are 80 and 80, then you got 160, so that top angle's got to be 20. So that's the reason why I use sine 20. That peak angle is sine 20. Therefore, L is equal to 10 sine 80 on sine 20, and it comes out to 28.8. So I got 28.8. Now, if you remember, I'm going to get rid of this. I don't want this anymore because it just adds to confusion. I have Q, which is this side right there, and I got W right there, and so I had W and Q, W on sine. I use the law of sines quite a bit. Equals Q sine 70. But I also had Q on sine 70 equals 10 sine 50. The law of sines is a very powerful tool. So I ended up with Q equals 12.3, and then W equals 11.3, and working my way up, I ended up using the law of sines for P, 13.5. The only time I used the law of cosines was trying to find Z. So I found P. I'm working my way up to find all of these different lengths using the law of sines. V, which is useless, I found was 10. G was 18.8. That was one of the sides. A, which was an important one. A equals 8.39. And Z, well, let's go to S first. S equals 2.8, 2.8, and F equals 3.05. Now, after having gotten all of these using angles, figuring out angles and using the law of sines to work out all of these different sides for this triangle, you could see I have all the sides labeled. Q, A, Z, F, W, P, T, V, G, M, and L, which is the entire side. I was able to work out all of the different sides. I know that this triangle here with X, we're trying to find X. X is the key. So in order to find X, again, it's the law of sines. I got, if I know Z, and I know sine of 50 degrees, then, and I know A, and I got A is a known sine phi, and that's also equal to F sine X. So once I know this, and I know this, or this, I can use, and in the case for me, I used sine X equals F divided by Z times sine 50 degrees. And then X equals the arcsine of F on Z sine 50. And that gets us the answer. So we need to find these sides on the triangle in the middle, right where X marks the spot, the inside triangle. This right in here, this triangle. So after using the law of sines a number of times, having started out with any arbitrary base, M, I was able to find pretty much everything except Z. Z posed a problem. That posed a problem. But I had A, and I had F, and I had one angle 50 degrees for that one triangle. And that triangle was sort of like this. And wait a minute, it's not like that at all. Sorry about that. How was that triangle? Let's take a look at that again. Yes. Yes. Okay. We're gonna, our triangle was sort of like this. We had that, and I think this was a little longer. And we had this, and then we had 50. We had F, and we had A, and we had Z, and X. So F was 3.05. A was 8.4.39. So what we needed was Z. Well, we used the law of sines to find Z, or cosines, which is Z squared equals f squared plus a squared minus 2 af cosine 50 degrees. And it turned out that z, by using that, we were able to find z, and z was, where did I have that? Z, 6.86. So I'm able to get all of these different lengths when I just arbitrarily use a side m equals 10. This is the key to the trick. And being able to just find all of the lengths of the different sides of the triangles that you've divided this thing into. And once we have that, then we have f on sine, let's see, f on, let's see, yes, f on sine, wait a minute, let's get this thing right. I had f on sine x equals z on sine 50. I gotta get that pencil. All right, so now we have sine x equals f on z sine 50. And sine x works out to be something like, I don't know, 0.34, something like that. We have 3.05 over 6.86 times sine of 50, which is something like 0.76. And once you work that out and take the arc sine, you have x equals 19.9 degrees. Now, Presh, Talwalker, he uses similar triangles and automatically concluded that x was 20 degrees. Well, when you just round this thing out to no decimal places, then you've got x equals 20 degrees. So I've got the answer. The problem is getting there, and the only way that I felt satisfied, I just intuitively could not see how that was a similar triangle. Once you make that assumption that it's a similar triangle, then the problem drops out easily. But I hate to make presumptions when I don't have a basis for them. And that's the problem I had with that problem. That there wasn't something that I could readily fall back on and say, yeah, that's obvious that the angles are similar, and therefore you can solve the problem readily. So I went a little bit more conventionally, and I just made an assumption that one of the sides had to be a certain length. I mean, I could have gone with M and tried to put everything in terms of N or M, but to me, having an actual number is a little easier to work with. So I just set M equals to 10, and then I started using trigonometric identities that I knew. Mostly the law of sines, mostly angle formulas, knowing that certain angles together sum up to 180 degrees, such as the interior angles for triangles. Once you know a certain number of things, you just apply them, and you're able to get the sides. You're able to get the other angles. And then in one circumstance, I used the law of cosines, which I used right in this spot right there. You know, the law of cosines is c squared equals a squared plus b squared, sides minus 2ab cosine angle c. And so that was the one thing I did was to find the side z, and once I had z, everything fell out, and I ended up with an answer that was probably actually more precise than the presumption that by making the assumption that there are similar triangles and defaulting that because there's similar angles, the angle must be 20. I just can't see. I just couldn't see it. I just couldn't see what they were talking about, and that bothered me. So I ended up defaulting to something more applicable. And, in the end, I end up with the same answer when you round out to the same number of decimal places, which is 0 decimal places. And I end up with 20 degrees. 19.9 rounds up to 20 degrees. And that was his conclusion, using similar triangles, was that the angle x was 20 degrees. But I just could not see how that individual... Now, you can go to his YouTube site. I readily invite you to it and check it out. But it wasn't readily obvious to me. And that's why I said, well, I'm just going to bear down and do the trigonometry and assign a side a value and work from there. And I did, and I ended up with an answer that is remarkably close. So with that, I think I'll just call it quits. I'll give you one more look at the triangle that I ended up in the end working with, and all of the sides that I ended up having there. You could see side W, side Q, side M, side P, side A, side Z, and F. The ones that are really important are finding F, A, and Z. And you do have to work your way up in order to get those angles. You need that triangle TZS, and so it's easier to once you got that triangle, you got the angles and you got the sides. You're able to then work out the problem. And like I said earlier, to me, for me to find Z, I was able to readily find F and A, and I just used the law of cosines from there. And it wasn't so bad. Wasn't so bad. So anyway, if you have any questions for me, any more, I think I approach this problem fundamentally more differently. I again made an assumption on the length of the side and then just worked my way through. It was tedious. It took a long time to do it, but I ended up getting an answer, and an answer that I can defend, an answer that I know for, as confidently that I got the numbers correct in my trigonometry, that I was correct. At least I know my approach was correct. And who knows, maybe the presumption that there was a similar triangle is wrong. I'm 19.9 isn't 20. It's close, but it isn't 20. And who knows, maybe my approach actually produced a more precise angle for X than the assumption that was made in the video on Presh Talwalker's site. So anyway, this is Fibonacci Man, Math Man. I like Fibonacci. In some circumstances, I call myself the Fibonacci Man because I am a particular. I have a very strong interest, almost obsession with Fibonacci numbers, but for the YouTube site, I call myself Math Man. So anyway, I'm wishing you all well. Stay healthy, please. This COVID crisis is not over. We're right in the middle of it. So, so long, everybody.